What if the ancient world's most advanced engineering never made it into a textbook, because nobody can fully explain how it worked? A weapon no army could counter. Glass that changes color in the light. Concrete that heals its own cracks. A lens ground centuries before anyone should have understood optics. 9 of them, built, perfected, and then gone. The deeper we dig, the stranger this gets. Number 9. Greek fire. In the 7th century, the Byzantine Empire was losing. An Arab fleet had the capital surrounded by sea, and there was no obvious way to break the siege. Then Byzantine ships began spraying a liquid fire across the water that kept burning even as it floated on the surface, clinging to hulls, spreading across waves that should have extinguished it. Enemy ships caught it and simply stopped existing. The siege broke. Byzantine sources credit a refugee engineer named Callinicos, fleeing the fall of a Syrian city, with bringing the formula to Constantinople. From there, the weapon was mounted on specialized warships called dromons, delivered through bronze siphons that let crews project the burning liquid directly onto enemy vessels, an early flamethrower, centuries before anyone had a word for one. For the next several centuries, Greek fire became the empire's single most closely guarded advantage. It was reportedly stored under the direct control of the imperial household, its production limited to a small circle of families who passed the formula down without ever writing the full recipe in one place. No captured soldier could give it up. No spy could steal what had never been fully committed to paper. That secrecy worked exactly as intended, and it is also the reason nobody today can tell you precisely what Greek fire was made of. Naphtha, pine resin, quicklime, sulfur. Historians have candidates, and multiple attempts across the centuries, both Arab and later Chinese, tried to reverse engineer something like it. None matched the original. Byzantium fell in 1453. The weapon that helped keep it alive for 800 years fell with it, and the recipe simply stopped existing anywhere on Earth. Which raises an uncomfortable question. How much of what we call ancient technology was never lost by accident, but hidden so well that even history could not find it again? Number 8. The Lycurgus Cup. In a British museum display case sits a Roman drinking cup carved sometime in the 4th century. Lit from the front, it looks jade green. Lit from behind, the same cup glows blood red. For most of the last 1600 years, nobody could explain why. The cup itself is a technical marvel even before accounting for the color-shifting effect. It is a cage cup, carved down from a single thick blank of glass so that an outer lattice appears to float, barely attached, around an inner vessel. A single mistake during the carving process would have shattered months of work. Roman glassmakers had no microscopes, no means of measuring particles smaller than a grain of sand, let alone controlling them. And yet in 1990, scientists finally examined the cup under an electron microscope and found gold and silver particles ground down to roughly 50 nanometers, a scale so fine that light itself behaves differently around them, scattering red when it passes through and reflecting green when it bounces off the surface. That is not decoration. That is nanotechnology, deployed by artisans who had no theoretical concept of what an atom was, let alone the tools to manipulate matter at that scale. Modern engineers have since tried to apply the same principle deliberately, experimenting with nanoparticle-infused glass for sensors capable of detecting trace chemicals or pathogens by the exact color shift the Romans achieved by accident, or by an unrecorded process nobody bothered or dared to write down. No second Lycurgus cup has ever surfaced. Whatever workshop produced, it appears to have made exactly one, and never again. Number 7. Damascus steel. Crusader accounts describe blades from Damascus so sharp they could split a silk scarf floating down through the air, so tough they could cut through a lesser sword without chipping. For centuries, this was treated as legend, the kind of story that grows taller with retelling. It was not legend. Damascus steel was forged from Wootz ingots imported from southern India and Sri Lanka along established trade routes, using a crucible process that produced a distinctive wavy, almost water-like pattern in the finished blade, visible proof of a molecular structure European smiths could not reproduce, no matter how closely they copied the shape or the hammering technique. Contemporary Viking-era Ulfbert swords, prized across northern Europe for their own unusual strength, were forged through an entirely different process and never matched the specific properties Wootz steel produced. Sometime around the 1700s, the supply of the specific raw ore used to make it, containing trace elements like vanadium that modern metallurgists consider essential to the effect, dried up. The technique, tied to that exact material, simply stopped being practiced. Within a generation, it was gone. In 2006, a team led by German researcher Peter Pofler used electron microscopy on a surviving blade and found something nobody expected: carbon nanotubes embedded in the steel's structure, wrapped around strands of cementite, a structure that gives modern steel some of its most advanced properties, sitting inside a sword forged by hand, centuries before anyone knew nanotubes existed. The smiths were not chasing nanotechnology. They were chasing a sharper, tougher blade and building it anyway. Number 6. Roman concrete. Roman harbors have sat in direct contact with seawater for 2,000 years and are, in places, structurally stronger today than the day they were poured. Modern marine concrete, by comparison, frequently begins failing within 50 years of exposure to the same conditions. For most of that time, the assumption was simple: whatever the Romans knew, it was lost the moment the empire collapsed, and modern concrete was simply a different, inferior trade-off for speed and cost. The material's most famous surviving showcase, the unreinforced dome of the Pantheon, has stood in Rome for nearly 2,000 years without a single steel rod inside it, something no modern engineer would attempt with today's standard mixtures. Then, in 2017, a team studying samples from Roman piers, built using volcanic ash imported specifically from the region near Pozzuoli, found something the ancient sources never explained. When seawater seeps into a crack in Roman concrete, it reacts with rare minerals in that specific volcanic mixture and grows new aluminous tobermorite crystals that seal the crack shut from within. The concrete does not simply resist the ocean, it uses the ocean to repair itself. Modern concrete does the opposite. Seawater corrodes the embedded steel reinforcement faster than open air ever could. An entire industry built out of steel-reinforced concrete may be structurally inferior, in the specific case of marine exposure, to a formula written down by Roman engineers 2 millennia ago, using a mixture that nobody thought to preserve once the empire that needed harbors no longer existed to build them. So the question is not whether the Romans knew something we do not. It is how much of that knowledge we are only now bothering to check. Number 5. The Antikythera mechanism. In 1901, sponge divers working under Captain Dimitrios Kontos, off the coast of a small Greek island, found the wreckage of an ancient cargo ship on the seafloor. Among the recovered items was a corroded, unremarkable lump of bronze that sat in a museum drawer for decades, catalogued and largely ignored. It was not until X-ray imaging in the 1970s and far more detailed CT scanning in the 2000s that researchers understood what they were looking at. Inside that corroded lump were more than 30 precision-cut bronze gears, interlocking in mathematical relationships complex enough to track the position of the sun, the moon, and possibly several visible planets, model the moon's irregular orbital speed, and predict eclipses years in advance using a cycle borrowed from Babylonian astronomy. Inscriptions covering the device's surface functioned almost like an instruction manual, listing star risings and settings the way a modern almanac would. Nothing else like it exists in the historical record for the next 1,400 years. The next known device with comparable mechanical complexity does not appear until European astronomical clocks in the 14th century. Some historians connect the mechanism's design to the school of Archimedes or to the astronomer Hipparchus, whose lunar theory the gearing appears to replicate almost exactly. Somewhere between the ship that carried the Antikythera mechanism and the medieval clockmakers, who eventually rediscovered gear-based astronomical computation, an entire branch of engineering seems to have simply disappeared. If ancient Greek engineers could build a mechanical computer 2,000 years ago, what happened to everyone who might have built the next one? Number 4. Heroes Aeolipile. In the 1st century, an inventor working in Alexandria named Hero built a hollow sphere mounted on a pivot, fed by steam from a boiling cauldron beneath it. Jets on either side of the sphere caused it to spin rapidly as the steam escaped, a working demonstration of rotational power generated entirely by pressurized steam. That is, mechanically, a steam engine, the core principle that would eventually drive the Industrial Revolution, sitting fully realized in Hero's workshop nearly 1,700 years before James Watt's improvements made steam power practical at scale. Hero did not stop at the Aeolipile either. His surviving writings describe a coin-operated device that dispensed holy water when a customer dropped in a coin, a set of automatic temple doors that appeared to open on their own using a hidden system of weights and siphons, and a programmable cart that could move along a predetermined path using a falling weight and a cord wound around its axle, a mechanical ancestor of the automated systems that would not become common again until the modern era. Hero's steam sphere was treated as a curiosity, a clever trick used to open temple doors or entertain a crowd, and nothing more. Ancient sources give no indication anyone tried to scale it into something that could power machinery or transport. The concept existed. The materials to build a larger version existed. What did not exist was the economic or social pressure to take a temple novelty and turn it into an industrial tool, so nobody did for over a millennium and a half. Number 3. Silphium. Before anyone had heard of the Antikythera mechanism or Greek fire, the ancient Mediterranean already depended on a technology of its own, a plant. Silphium grew wild in a narrow strip of land near the Greek city of Cyrene, in modern-day Libya, and it was used as medicine, seasoning, and, according to Roman sources including physicians in the tradition of Hippocrates, a remarkably effective form of contraception. It was valuable enough that the city minted coins stamped with an image of its seed pod, a heart-shaped silhouette some historians suspect is the actual origin of the heart symbol used today. Every attempt to cultivate it outside that narrow strip of coastline failed. Silphium would only grow in its native soil, under conditions nobody could reproduce elsewhere, no matter how many attempts Roman botanists made. Demand for it, meanwhile, only grew, driven by an empire that prized it in recipes recorded by writers like Apicius and wanted more of a resource it could not replicate. Overgrazing by livestock on the same narrow coastal strip likely compounded the pressure already put on the plant by decades of harvesting. By the 1st century AD, Silphium was reportedly extinct. Pliny the Elder wrote that the last known stalk was presented to the Roman Emperor Nero as a curiosity, because by then, that was all that was left of it. Every other invention on this list vanished, because knowledge was lost, hidden, or simply never scaled. Silphium is different. It vanished because an entire ancient economy consumed it faster than it could grow back. The only entry on this list wiped out not by secrecy, but by success. Number 2. Viking sunstones. Norse sagas describe Viking navigators crossing open ocean under skies too overcast to see the sun, using something called a sunstone to find their bearing anyway. For centuries, this was treated the way most saga details are treated, as legend, embellished in the retelling, probably not literal. No physical sunstone had ever been confirmed in the archaeological record, which made it easy to dismiss. Then, in 2002, a chunk of Iceland spar, a naturally occurring calcite crystal, was recovered from the wreck of a 16th century English ship near the island of Alderney, stored alongside navigational instruments in a context that made an ornamental purpose unlikely. Researchers, including French physicist Guy Ropars, tested it and found something the sagas had described without any modern vocabulary to explain. The crystal splits and polarizes light passing through it, revealing the sun's position even when it is fully obscured by cloud cover or already dipped below the horizon, accurate to within a few degrees. A working solar compass, built from a mineral, requiring no batteries, no needle, no magnetism, functioning on a principle of light polarization that would not be scientifically described in Europe until the 1800s. Viking sailors may have been using it a full 1,000 years earlier to cross open ocean toward Greenland and possibly North America, centuries before magnetic compasses reached Northern Europe at all. Number 1. The Nimrud lens. In 1850, archaeologist Sir Austin Henry Layard, excavating the ruins of an Assyrian palace at Nimrud in modern-day Iraq, uncovered a small oval piece of rock crystal, ground flat on one side and convex on the other. Catalogued at first as a decorative object, possibly ornamental, possibly ceremonial. Nobody expected it to be anything more than that. Conventional history places the invention of the optical lens in the 13th century, when eyeglasses first began appearing in Europe. The Nimrud lens is roughly 2,800 years old. When researchers examined it more closely, they found a precisely ground surface capable of focusing light and producing actual magnification, the defining feature of a functional optical lens, not a decorative curiosity. One early theory suggested it may have simply been used to start fires by concentrating sunlight, but the lens's specific focal length makes it a poor fit for that purpose, and a much better fit for close magnification work. Nobody knows exactly what it was used for: a magnifying tool for fine engraving on seals and tablets, an aid for a court astronomer, possibly even a rudimentary viewing device, a claim some researchers have floated based on Assyrian astronomical records that describe observations of the night sky in detail, difficult to explain with the naked eye alone. Whatever its purpose, someone in ancient Assyria understood how to shape crystal into a working lens millennia before the rest of the world caught up, and whatever knowledge produced it disappeared along with the civilization that made it. 9 inventions, 9 different centuries, 9 different corners of the ancient world, and in every case, the same pattern. It worked, it disappeared, and it took the modern world thousands of years to either explain it or build it again. Thanks for watching. Don't forget to subscribe for more ancient mysteries and impossible discoveries.